All right, so maybe we'll try to do a less hectic game this time and actually talk about some climate
Sounds good.
models.
Twitch.tv/climate.
Do you know the actual history of like the individual papers that like developed zero-dimensional climate models from the beginning?
No, I wish I did. I
Yeah,
was
I
thinking I
don't
should
really know
read
it
some.
either.
I know a rough timeline of like the Manabi stuff was, I guess, in the 60s.
Oh, I was
Um,
talking like way older, like
way before. Oh
the
no,
zero D like sun and
like the
rock.
early 1900 stuff.
I think even like in the 1800s they were already doing some of that stuff, but yeah, definitely in the early 1900s.
Yeah, unfortunately not. There's all these
All right,
things I
we
wish I
can
knew.
just guess.
Okay.
Um, okay, so I think like the earliest climate models that I know of are basically just you have a model of the sun, which you just assume has some like power output, and
Uh-huh.
then you basically like have that coming in from the sun into the earth, and then you take like the basically the cross section, or like a circular cross section of the earth, and then that's how much energy is coming in from the sun, and then
Mhm.
you just balance that out with outgoing radiation that follows the like Stefan Boltzmann, uh,
Mhm.
you know,
Blackbody radiation stuff.
yeah, like proportional to temperature to the fourth. And so basically you can find some equilibrium temperature for that.
Mhm.
And that actually works pretty well if you assume that some of the light gets reflected. So like even for a surface like the moon, a decent amount of that solar radiation gets reflected. And if you just have a model of that with those three components, just reflection from the lunar surface and like incoming solar radiation and outgoing blackbody radiation, you can actually get a pretty good estimate of temperatures
Mhm. Yeah,
for
these
some
these are
celestial
things.
bodies.
Yeah, you can. That's a good point. You can do this for any celestial body, and this is probably just a few equations on a piece of paper that you can write out.
Yeah, I mean this is
I
like a
think we.
problem set we do like for the first
Yeah.
class in our climate classes.
Yeah, I think we did this in my radiation class. Like you said with Stefan Boltzmann. So that, I mean, yeah, I mean from the little reading I was doing about the timeline of climate modeling, I think you're right that was as early as the 1890s, which is pretty cool, and it, and
Yeah.
it gets a good estimate.
Yeah, and it gets a really good estimate for bodies without an atmosphere. And then once you have an atmosphere and you have different gases that can absorb some of
Uh-huh.
the either the incoming, they can either absorb or reflect some of the incoming solar or the outgoing like heat radiation. Um, and okay, I need to focus on looting, but basically, then you start getting into the complexities of sort of early climate modeling efforts where they're trying to figure out how all these different chemicals in the Earth's atmosphere, like water vapor and CO2 and methane and all those things, interacted to give you the actual climate we have on Earth. And a useful thing for those first studies was using other planets that we know. You could use other planets if you know their temperature and know their atmospheric constituents as sort of test cases for some of these theories. So like
Hmm.
predicting the temperature of Venus's atmosphere was a pretty big, um, a first challenge and then later success of climate modeling.
Yeah,
And
exactly.
I think in like either the 70s or the 80s, they even sent some probes deep into Venus's atmosphere to check what the like full temperature structure was, not just at the top of the atmosphere, but all the way down to near the surface. And I think they were able to predict some stuff pretty well and other things not well, and we learned some stuff from that.
Hey, there's a. Do you have a shotgun?
No,
Okay, there's one right where I am right now. Do you need one?
cool. Oh yeah,
Yeah, I think an important definition too is just like model in general. And we think of mathematical models. When you say climate models, we think of these monster things with all these, tons of equations and interacting parts. But those very early climate models, which, like we said, could be represented by one or two equations, are just as much models as the complex ones these days, because it's a simplified mathematical representation of the real climate system.
Yeah. Oh my gosh.
Right.
They changed how these like cars and stuff interact with buildings. Now the buildings destroy everything.
I'm doing decent. I just need some materials here.
Yeah, you want to go over to Haunted Hills on our way
Yeah,
to the
let's do
zone?
that. Let me grab this chest here.
Sure.
I've got a big potion for you.
Cool. Okay, so let's see. I think the first like these zero-dimensional models, which basically just have incoming solar radiation. Let's see, absorb incoming solar radiation, some fraction of that being reflected by the surface, and then just like being balanced by blackbody radiation. That was like the early 1900s, and then I think sort of maybe like in the 50s or 40s, they started adding greenhouse gas absorption in the atmosphere. And so I think that's sort of when it becomes a one-dimensional model, where now you have several different layers, not just the Earth's surface or the top of the atmosphere, but also some middle layers of the atmosphere have their own temperature and they're emitting and absorbing radiation.
Okay, so you actually have an explicit layer for ozone, and you're actually resolving, or rather modeling, carbon dioxide and stuff like that.
Yeah. And then I think at first they didn't really have like, they weren't actually, it was sort of like qualitative things, like there was just some number that could vary between 0 and 1, which controlled like how much these gases were emitting and absorbing. And then later they realized that you could actually directly model, like if you knew the equations for how much each of these gases emits at a specific wavelength, if you like integrate over the whole wavelength of the solar spectrum, you can actually directly calculate these things. But I think at first it was sort of like a qualitative estimate of what happens if you have more of these gases or less.
Sure.
And then you can start adding things like clouds, which they sort of act similar to the surface in that they can also reflect some radiation. You know, a cloud is a very bright thing that reflects a lot of the radiation that comes at it. So adding even a small fraction of cloud cover can actually change the energy balance of the planet quite a bit.
Yeah, and imagine with these very early models, it was similar to the greenhouse gas implementation, where you just say, you know, at this latitude, you know, around the equator, there's, you know, over this band, you have this weighting number, like you said, between 0 and 1 that reflects radiation.
Yeah, I mean, I think at this point we're still talking one-dimensional models, so they don't even have like different latitudes. It's still just like integrating over the entire planet, and then sometime in like, I don't know, maybe the 50s or the 60s, they start having latitudinal dependence. And when you have latitudinal dependence, now you have to start thinking about how much heat gets transferred from one latitude to the other by the atmosphere.
And you can't really do that. I mean, how did they do that before?
Well, again, you can give it like a number from like 0 to 1 for like sort of how efficient the atmosphere is at doing these things, but it's not really based on any physics at this point.
But based more on qualitative factors, based on how they know the Earth system works.
Yeah. Or yeah, you can like sort of tune it to match what you think the atmosphere is doing today, for example.
Hey, let's get away from this fog.
Yeah, good call. All right, I've got some pretty good. I need a better SMG and assault rifle, but I've got a sniper and a shotgun.
Okay, yeah, I'm pretty much on the same page there.
But yeah, so then once you get to this like latitudinal structure thing, you're getting pretty close to having like a reasonable climate model. So these models could do pretty good at even estimating like climate sensitivity, which is how much the climate would warm if you double CO2. And so like the like first Manabe and Weatherald model was just one of these one-dimensional ones. They didn't even have latitudinal dependence, and that one actually estimated a climate sensitivity, so how much you warm the planet by doubling CO2 in the atmosphere, and it gave an estimate of like 2.3 degrees Celsius, which is pretty close to what we think it is today. It's like right in the middle of our plausible range. So it's kind of amazing.
It's really impressive that, that just basic radiative balance will get you a lot of the way towards climate sensitivity for
Yeah.
CO2 doubling.
And I mean, that model did have things like vertical convection. So it, they knew that like in the lower atmosphere, if you heat the surface enough, then the air's going to rise and it's going to like mix up the lower atmosphere. And that did make a difference compared to some earlier models. And they also had things like, as you warm the planet, they acknowledge that that's also going to cause the air to take up more moisture. And since water vapor is also a greenhouse gas, that's going to amplify some of the warming.
Yeah. So, I mean, I would argue then that these early climate models, the main questions are really of global radiation balance. So, what's the equilibrium climate sensitivity? How does this relate to radiative imbalance and aerosols and greenhouse gases? But I guess what would motivate them to develop these things further is more regional questions about mechanisms of things like the Gulf Stream. But that's ahead of ourselves. More atmospheric things like the Hadley cells. Because you get a lot of the big questions. To your point, you get a lot of these big questions sort of addressed just with a very simple 0 to 1 dimensional model.
Yeah, I wonder what, if you like look back then, I wonder what was the big motivation for going 3-dimensional for them. Because in hindsight, we know all these things, but I wonder how much they actually.
I'm sure we could dig up papers and skim some intros, right? I mean,
yeah, kind of interesting.
There's this sort of, for any subfield, most of these papers that are citing each other have similar introductions, and they say this is what's motivating this body of literature. And yeah, I am curious what the big motivator was to start trying to explicitly represent the circulation of the atmosphere. Also, we're down to 19 people, and I haven't seen anybody.
Yeah, I know, that's kind of crazy.
Should we try to post up somewhere? We're inside the circle.
Hold on. Wait, Teriyaki, is Pardis Prime also talking in chat? I don't see. The first message I saw was you saying that.
What's that?
I was talking to the chats on the viewers. All right, you want to go on this high ground?
Yeah.
Do you have a sniper too?
And I've got a hunting rifle, which I'm not very good with.
Yeah, Pardis, you can join the Discord channel. Thanks for linking it, Teriyaki.
Oh, this high ground. Yeah, that's great.
Yeah. Yeah, so I guess so the way that they eventually made it to 3 dimensions is pretty cool. So at the National Ocean and Atmosphere Administration, or NOAA, at one of their labs in Princeton, New Jersey, they were working with some people at the Princeton Institute of Advanced Study, which is where like people like Einstein spent some time. It's where like one of the first computers was built. That's where they first invented like weather forecasting, and so they were working with those people, with like the weather forecasters, to build the first 3-dimensional numerical climate models.
Yeah, I guess it's important to say that sort of concurrently at this time, we're looking at these big one-dimensional models trying to simulate the globe, and at the time, people are already the weather community is advancing pretty far into numerical models, so they're actually explicitly resolving atmospheric circulation, and these are the ideas that informed trying to bring that up to the scale of a global climate model.
Yeah.
Because this thing didn't exist in a vacuum. It was kind of these.
I don't know if there were. I don't know if weather forecasters were actually having much success yet in like the 50s and early 60s, but they were at least trying.
Yeah, they were at least paving the path with actually, trying to solve, the fluid equations. And I think it was I was reading a timeline, and what I thought was really cool is, NCAR in Boulder, the National Center for Atmospheric Research, was focusing on numerical weather prediction, and I think in 1960 it was a big timeline event where NCAR founded their climate modeling division, and now that's kind of what NCAR is mainly associated with. That became a behemoth, became one of the U.S.'s big climate models.
Yeah. Wow, where is everyone? This is kind of ridiculous.
I don't know, but I think we can win by talking about climate science in the corner of the map.
Yeah. Okay, the last thing I wanted to say about the three-dimensional climate models is that there's these people at GFDL working on it, and at first they were working on the ocean model and the atmospheric model separately. Oh, these guys have a fortress over there.
Yeah.
Um,
My hunting rifle's not going to touch that.
I'll take him out. Don't worry.
All right.
I don't see anyone. And so they're working on the ocean and atmospheric model separately. And then it wasn't until like I think 1969 the first time that they were able to couple these two models together and actually have like a global climate model.
Yeah, yeah. Well, I think we should step back because we were just talking about
the
radiation models and just talk about what you mean when you say three-dimensional model. So this is going from sort of that radiative, radiation comes in, some gets reflected, some gets absorbed, some gets re-emitted, and you balance that. But the big thing about a three-dimensional atmospheric model where we started is you start to actually think about latitudes and longitudes. You break up the globe into grid cells. So you partition the globe into individual grid cells, and you start to explicitly code the basic laws of physics that we know. And you think about things like, we're getting shot at.
No, there's usually someone else.
Okay.
But I do see them. All right, we're gonna try and snipe this guy.
Yeah.
Nope.
Oh, it ain't happening for me.
Well, now they know we're here. That's good.
Yep.
All right, actually, I don't think they do know we're here.
Yeah.
Oh, also, they're out of the storm, I think. Oh, they're barely on
flying.
it. Well, actually, no. I think they are, maybe. Well, I don't know. It's hard to tell.
Oh, behind us.
Oh, okay.
Oh, man. Oh, shoot.
Just gonna throw some, let's try and blow him out of the sky. What is it? Being held
Right
up by?
above us.
Oh. Oh, yeah.
Oh, he dropped down. Oh, right behind me. Oh, no. Dang it.
Oh, I don't see him. Oh, no.
He's
Oh, I see him.
he's coming up behind you. Nice.
Oh, God. I fell. Maybe to my death. Oh, my God.
He knocked me out. It's all right.
Oh, my gosh. He didn't die. Oh, God. He got me. It's not bad. It's top 6.
No, man. That's two good games in a row. One with a lot more kills.
Yeah. All right. Let's get to some of the questions that people have been asking in chat.
Okay.
All right. Yeah? Did I have a slurp juice? My roommates are watching from the living room and they're yelling at me. Okay, so
we were thinking about atmospheric models. We couldn't handle it.
Yeah. That was actually a pretty good fight at the end. Okay, so Teriyaki was saying this is a good time to ask about equilibrium climate sensitivity, or ECS. And why Andrew Dessler thinks it's above 2, but hard to quantify the top end. Okay, I actually know a decent amount about this, so I can answer that.
Yeah, this is on you.
So equilibrium climate sensitivity was defined in these early climate models by basically taking a climate model and you try and match it to today's climate as closely as possible. And then all of a sudden you double CO2 in the atmosphere. And then you wait and look at, once it sort of steadies out again and reaches an equilibrium, how much did the climate warm on average? And that number in degrees Celsius is the equilibrium climate sensitivity. So part of the problem with this number in terms of interpretation is, depending on how fancy your climate model is, the number can be totally different. So for example, if you have a model like the early one-dimensional climate models that don't have an ocean, they're going to warm up. First of all, they're going to reach their equilibrium much faster because the ocean's not taking up much temperature, but also they don't have all these climate feedbacks, like the fact that as you warm, you're also melting a ton of ice, and That's going to lower the albedo of the planet, so you're going to take up more solar radiation. Anyway, so equilibrium climate sensitivity already is pretty variable between models, so that's one issue. The second issue is originally I think it was defined for models, but then people were like, okay, but we have some observations. Let's see if we can try and compare the model estimates to observational estimates. And so by looking at the Earth's energy budget, usually the way you do this is you know how much solar radiation is coming in. You know how much the planet's warming, both the oceans and the atmosphere, although really it's the ocean heat content that matters because 90% of the extra heat goes into the oceans. So by looking at this heat budget, you can basically estimate what this climate sensitivity is from observations. And what happened is there's the modeling literature, which basically for the last, like, I don't know, 50, yeah, probably for the last like 50 years, they've said that the climate sensitivity is between like 1.5 and 4.5 degrees Celsius. But then the observational estimates are almost entirely on the low side. And so like some of the most famous ones are like a 1.2 degrees warming per doubling. So then there's this big question of, are the models running too hot because they don't agree with observations, or is it there's something wrong with the observations? And it seems like in the last 5 years that question is starting to be resolved, and it's actually kind of obvious when you think about it. So the way that they do it with the observations is they look at like the last 20 or 30 years of observations, and they look at how much warming there's been by some change in the amount of forcing. So how much you are like acting to heat the planet by adding CO2 or other types of forcings. But anyways, the actual so the problem with that is that these feedbacks I talked about, like the fact that when ice melts you lower the albedo, or the fact that as you warm the Arctic you're starting to release permafrost, these feedbacks haven't actually kicked in yet. And so what happens is if you try and compute, if you take like a 20 year chunk of the climate and you try and compute the equilibrium climate sensitivity just from that, it's going to give you a number that's too low, unless you're doing that sort of towards the end of the climate's equilibrium process. So like probably what would happen is if you made the same types of calculations from observations people are trying to do today, and you did them in like the year 3000, they would get a much higher number for the climate sensitivity. And so that's why I think we no longer really believe the observational estimates. Also, in the meantime, people have made similar estimates from paleoclimate. So you can say, okay, we know that, for example, between the peak of the Ice Age and today, they added another 100 parts per million of CO2. And so that's another way where you can use the observations, in this case, paleoclimate. Oh, okay, on my way. To try and estimate climate sensitivity. And the paleoclimate ones are super high compared to observations. So that's probably why Andy Dessler, nice. Oh, dude, you're a hero. You just get both of them?
Oh, no, just one.
On my way.
Oh, man. I'm almost dead.
Alive. Stay alive, stay alive. I'm almost there. Where's this guy?
Right behind me. Right here.
Oh my god.
Right above you. I got some shots on him, though.
Yep, got him.
Nice. All right.
Good job, dude. Oh, I just heard someone else, though.
Yep.
Oh, God.
And behind you. Oh, boy.
Oh, my God. That's rough. Okay. Well, that was a pretty fraught definition of equilibrium climate sensitivity.
So, if I understood you correctly, with these like 30 to 40 year observational timescales, would low frequency internal climate variability play a role too, like the Pacific Decadal Oscillation?
Yeah, for sure.
AMO,
and that's
like
a big part of the literature too. And I'll link some. There's 3 papers I'm thinking of in particular that have come out in the last like 4 years that I'm referencing by like Peter Hoybers is one of the groups, and Christie, I forget his last name, but at Harvard he did his PhD on this topic, and then Kyle Armour at University of Washington has worked on it. Kate Marvel at Columbia has worked on this. But I'll link those in the Discord later.
Cool.
All right.
Yeah, I hadn't heard much about the observational estimates for this. I was just familiar with the model experiments.
Okay.
Yeah. So if there aren't any other questions, do you want to?
There are questions, so I'm in the chat right now.
Okay. Yeah, I can't see it, so.
Okay.
So Partis Prime wants to talk about
the social science tied to climate change.
Okay.
Yeah, let's go Haunted. Thanks for the bits, Laiku. All right. Partis Prime says, speaking as an American whose entire life is predicated on the easy availability of fossil fuels, true. I'm worried about plans to divest ourselves of them. I certainly want to do it. They're worried about they're worried about any plans to divest ourselves of fossil fuels. So I think presumably the fact that we don't have electric car charging stations widespread enough for most people to transition to electric cars yet. Not to mention that they're also pretty expensive. And other ways in which it's really hard to completely divest from fossil fuels today. And they certainly want to do it, but they're worried about how difficult it will be to sell it to people. I think the big part is just getting the cost down. I mean, we're already at a point, and I can try and dig up some of these articles, but in large parts of the U.S., wind and solar are cheaper than any other thing, any other source of energy, including natural gas, which is like dirt cheap right now. So I think that on its own gets you pretty much, at least for energy production, that gets you a large part of the way there. That doesn't really help transportation and agriculture, but it does, energy production is like a very large fraction of energy consumption in the U.S. And then I think, it might not be as fast as we wanted, but we do have a bit of time. We have until 2050 to get to near zero carbon if we want to avoid like 2-ish degrees of warming, probably a little bit more than 2, I would guess, but you could still get to like 2.3 degrees of warming if we get to near zero emissions by 2050. So I think it's in the realm of possibility, as long as we don't like actively subsidize fossil fuels, which we are doing.
Well, there's also issues with things like placing tariffs on importing, solar panels to the country.
Yeah,
which drives that industry to a difficult place.
And agriculture it's one of the worst greenhouse gas producers, but it's still only like 20% of the global estimates, I think. It might be more than that in the U.S. Alone. People get really confused by this because there's sort of a lot of different numbers you can pick for like impact of a sector on global warming. And if you just pick the right one, you can make it seem like agriculture is like the devil and responsible for 80% of the warming. But if you just look in terms of like how much warming will each sector produce by like 2100, agriculture is like something like 20%. So it's not that.
Can you hear? All right,
Yeah.
My computer's put to sleep. I thought I lost this. All right.
Nice.
Good, we're still here. So I didn't see your audio cut out while I was asleep, but I was gonna say with regards to.
Here, let's get out of here, dude.
All right. With regards to animal agriculture, I think the interesting sort of studies are on lab-grown meat, and I think people at first would think that society would think that was gross, but there's been a lot of studies that have come out that show most
we just
people are
walked by his
totally.
chest.
Oh really? most people surveyed are like completely on board with lab-grown meat, which solves a lot of the issue of you know, ruminant emissions from cattle.
Yeah. I think someone that I had on Climate Fortnite was telling me that the lab grown meat like might be carcinogenic, and now it kind of spooked me, but I didn't actually look into that claim. I should probably check that, but
I have no idea.
I like almost bought an Impossible Burger at a restaurant the other day, and then I ended up getting something else.
Are they already out?
Oh
or is
yeah,
that like a
Boston's all
plant-based
about
burger?
that stuff, dude.
Oh,
The
yeah?
Impossible Burger.
Wait, oh, dude, I just killed
Oh
that
yeah, you
chest.
did. That's okay.
Even I've not seen these in Boulder even, and you'd think Boulder would be on it.
Oh yeah, Boston. I mean, Cambridge especially is all into that stuff.
That's funny. So this is lab grown. This isn't plant based. This isn't like the beet burgers.
I don't actually know.
It might be like
I
the
don't
beet
know what
burgers that you can get. Like Whole Foods has those bars.
No, it's not beet burger. It might. I think it's these ones where they like take vegetable proteins and then like they like mess with the protein so that they like produce hemoglobin or something. So it actually like ends up being like a bloody burger even though it's vegetarian. But I don't actually understand biology very well, so that's probably wrong. Someone was trying to explain it to me last week. Okay, yeah, Zoiku knows the facts.
Okay. Oh man, it's
Impossible Burgers are plant-based. Okay.
they are okay. Yeah, there's these like beet burgers that bleed beet juice. I don't think lab grown meat's on the market or even close to it yet.
But I think even these like things where they manipulate the proteins, someone was telling me that they might be carcinogenic. But I should probably stop spreading that rumor because it's probably wrong.
Yeah. I mean, but on the note of, I can't remember the original question, but it was surrounding reducing carbon emissions. But I mean, one way for the average person to reduce their footprint is just to eat a little less meat, or to try some of these beet burgers, I guess.
All right, Zoiku, I'm giving you the task of determining whether or not these things are carcinogenic. Since you're the expert.
I cannot get this, since it fell asleep, I can't get this projected back to my monitor, so I'm playing on like a 13-inch MacBook screen right now.
I mean, that's not that bad. I'm playing on a 15-inch screen, so.
Alright, so we're good. Dude, I have the worst luck in these areas.
Yeah, we didn't do so well at Loot Lake earlier.
Yeah. Oh boy.
Okay, a soy gene to try and mimic the bloodiness of a real burger. Interesting.
Yeah. So, hey, whatever gets people eating it.
All right, you want to go to this high ground up here?
Yeah,
it's gonna be a long climb. Need a grappling hook or something.
Yeah. I don't have a ton of mats, but I have some. Can jump from out here. Oh no. Alright.
I got this one.
Alright.
Oh no.
Alright, let's talk about coupled models if
yeah, sounds good.
If there's other questions. So a while ago when we were in a battle a few games ago, we were trying to build up from the radiative balance models to a 3D model, and what I was talking about is just how you get there, and that's by dividing the globe into a bunch of grid cells, and in the grid cells of, you know, early days, very coarse. Oh no!
That's okay, I caught myself.
All right. In the early days, they were very, very coarse grid cells. I imagine, you know, order 300, 400 kilometers.
Oh my god.
This is a very cool spot, by the way.
Yeah.
There's like diving boards for.
Have you never been up there?
No, I'm these days I'm only playing when I'm on here with you.
Okay.
Recently. Yeah, but so in these grid cells, you just basically encode the basic laws of physics that we know, and we call them the primitive equations. So you just put in continuity laws that you learn in, you know, your first physics class, like conservation of mass, conservation of energy, conservation of momentum. Obviously, a little more complex than what you learn in physics class because they're written as differential equations. But basically, a few simple physical equations, and then you start the model off in some state, usually from observation, so you can put in observed temperature of the atmosphere, and I tend to think ocean, so I was just going to list off a bunch of ocean variables, but we're still talking atmospheric. But you initialize the atmosphere with observations, and then you just start solving it in time steps. So you just push the model forward step by step, just solving these equations, and it pushes fluid around. And it, you know, you don't hard code anything. You don't hard code the Hadley cells or the intertropical convergence zone, you just hard code basic laws of physics and push the model forward, and these things start to develop in it. And so the first models were super coarse, and they were just looking at, they call them general circulation models, and they're just looking at atmospheric flow. Let's see. And then from there, I mean, you started talking about the coupling, which is really intriguing. And to me, all an ocean model is you just take that atmospheric GCM, the general circulation model, and you flip it upside down, and you couple the two together, and you crank up the density a lot. So you go about 1,000 times higher in density of the fluid. You add in some continents and some bottom topography, and it's the same fluid equations. You know, that's the unique thing. They've just got different density, which really drives the differing flow. You know.
Yeah. And so that was
On a basic
basically
level.
that was like the state of the art until probably like the mid 80s, and that's when people sort of went beyond just modeling the airflow in the atmosphere and the water flow in the ocean, and they started adding things like biology. So you have all these different nutrients swirling around. Oh, dude, we gotta get the hell out of here.
Okay, here, get in. Is this gonna kill me?
Probably.
No, dude.
Oh my god. All right, let's go.
All right.
We're not gonna survive unless we.
I don't have a launch
we're gonna
pad.
need this thing, dude.
Okay, let me get in. Oh no.
Oh, dude. Oh my god. All
Right,
right,
go.
go.
Yeah.
All right, we're rolling.
Nice. Well, so one level I skipped, which you were just talking about with your work on the early CMIP-1 climate models, which we can talk about in a little bit. But the early atmosphere ocean models, they just treated the ocean, they call them swamp models. So the ocean was just this big swamp that evaporated water, served as a heat reservoir and water source. And if anything, they just modeled like the upper 100 or so meters and allowed it to absorb and redistribute heat just in that surface layer. And then the next big thing when we had the computational power was to have the ocean actually in 3 dimensions and allow the development of deep ocean currents and, you know, things like the Gulf Stream. And let's get out of there. But it was another whole level to actually start resolving ocean currents and deep ocean circulation like you study.
Yeah, and so that was a lot of work being done in like the late 60s and 70s. And then the 80s, they started adding things like nutrients and some very simple biology. So like phytoplankton.
I wouldn't say the biology is much more complex still. We just, the common climate model right now. And so you go from GCM, general circulation model, to ESM, Earth system model, when you start resolving things like biology and nutrients. But now the standard model has 3 phytoplankton types and 1 zooplankton type, and that's about it on the biology.
But I think that's a big step, though, going from just phytoplankton to having predators that can now interact.
Yeah.
And
they can take these output and feed them into independent fisheries models as well. So, I mean, there's
it's pretty cool
here, of course. But you're right. And I mean, we're pushing right now, the community is pushing for more phytoplankton because various phytoplankton species are important for the carbon cycle in different ways. Like, for instance, there's this species called Phaeocystis that produces dimethyl sulfide, and that can leak into the atmosphere, and it's a greenhouse gas. And then there's things like coccolithophores that build calcium carbonate shells. They affect the carbonate system in the ocean. So you have to separately model these things to actually get the independent impacts of these microorganisms.
Yeah. All right, let's take a quick break to answer Teriyaki Source's question.
Cool. Also, we're in a good spot. We should get up on this hill or something.
Yeah, we should. Yeah, how are we doing so well these games?
I was just not paying attention.
Yeah, that's the key. That's the tip to all you Fortnite players out there. Just start talking about climate science and you'll be in the top 10 easy.
All right, I've got a sniper this time.
Oh,
so.
Nice, dude. Free achievement.
Oh, let me do that. Cool. Ooh, I do not have mats, though.
Uh-oh, we're getting shot at. I don't know where we're... Oh, don't peek, dude. Alright, Teriyaki, I'll answer your question after this game, since we're getting towards the end. But yeah, so Riley, now that we have the Discord server, is a much better place for like posting, like people have discussions after the streams, and we can post papers and discussions. It's pretty cool.
It's nice. Yeah, I have some links pulled up that I wanted to drop in, just sort of intro to climate model links from GFDL, and they're pretty nice. I hear people around us.
You do? Okay.
kind of. I have a trap. Should I just put it here in case we die? It
Um,
won't. It doesn't do allies, right?
It depends how. No, it doesn't. But if you're quick? Oh god, that's a grenade.
Shoot.
They're charging us. Oh, him for 60.
There's 2 of them.
Oh man, he got me. Nice. Oh, close.
1 down.
Good try.
All right, let me see if I can get my monitor back up.
All right. So Teriyaki-saurus said, Dr. Dessler mentioned climate engineering such as stratospheric seeding as a plan B for certain thresholds. Do we already know what those thresholds happen to be, either via model or geological data? So this is kind of a trick question, and I think something that climate scientists have not done a very good job of communicating, which is the fact that these thresholds in the climate system, they're not like a hit or miss thing. It's not like once we go to 2.2 degrees Celsius that all of a sudden Greenland's going to collapse, or like all of a sudden when we get to 3 degrees
continuous
that
spectrum.
all of the methane clathrates are going to shoot out of the Arctic Ocean. But that said, there is a difference between 2 degrees Celsius of warming and 3 degrees Celsius of warming. And so if you think you're going towards 3 degrees, but you can do some kind of geoengineering, like, injecting sulfates into the stratosphere to reflect sunlight, you can put off that 3 degrees of warming. The question is the cost of that worth what you're gaining and reducing the warming, and also whatever potential risks there might be, because we don't really know what's going to happen if you inject a buttload of sulfates into the stratosphere, and we can try and estimate what the risk is by trying to simulate it in climate models, but there's always a chance that there's some process we're missing in the climate models that would happen in real life. I think that's why people are still kind of scared of most of those geoengineering ideas being taken seriously.
Yeah, but you bring up just one point to hit on. I'm gonna give it up on this monitor, so forget it.
Do one more, and then I'll switch over to Eco.
Okay, cool. What's that?
Oh, it's this new game. It's awesome. It's do you ever play Minecraft?
Yeah.
So it's sort of like Minecraft, except it has like a climate model engine, basically.
Oh, cool.
It's nuts. So like as you develop so you start just with no resources, and you chop down trees and mine stone, and eventually you can like smelt iron, and like eventually you can actually do things like build cars and like produce gasoline. But as you do all those things, you're emitting CO2, and that's actually like feeding back onto the climate. And so things like the temperature's warm, and it changes the ecosystems, like the like forest ecology, and also like melts snow on the top of mountains.
Wow. So they've actually got, the engine has a response to CO2.
Yeah, and then like sea levels rise, and so you can like flood your town.
Oh wow.
It's pretty nuts. I just started it on Sunday.
Is it on Steam?
Yeah, it's on Steam. It's $30, but the developers of the game kindly gave me a couple keys that I can give to some of our recurring guests. So if you
cool
if you want in on that, we can probably get you one.
Yeah, that would be nice. That sounds really fun.
Let's go here. Is that the billboard?
Right, cool. Yeah.
Okay.
So one thing you had just mentioned casually about the sulfate aerosols, you said we could test this in climate models, and one thing I like to talk about is, I remember when I first started using output from climate models, they were kind of this magic thing. I was an undergrad. I was just, doing it for a small project, and you're just dealing with this data, and you don't really think much about where it comes from. And I think I always associated climate models with just, they are always running these greenhouse gas scenarios where CO2 emissions are increasing, and you see how the world changes. But based on what we were just talking about earlier, they're based on.
I'm gonna drop this billboard.
Okay. You just put in each grid cell. You just solve the basic equations of physics. Because of that, you can push the system in any way you want. So one interesting experiment we can do is increase the CO2 because that's super societally relevant. But you can also inject sulfates into the upper atmosphere. You can also drop nuclear bombs in it, or cause large volcanic eruptions, or model the paleoclimate. Ooh.
These guys are coming. Do you have a gun?
Here. I got nothing.
Oh yeah, we're down.
No.
That guy's
Oh
good.
no. No, sir. Oh.
All right. Do you want to finish your thought while I get eco set up, maybe?
Yeah. Oh man. I had auto run on. I was stuck. Oh boy. Yeah, no, it's just basically that the beauty of these climate models is we impose the basic laws of physics we know on them, and then we can experiment them in any way we want. So we can ask questions with them, and we use them for a variety of tools. I mean, my first paper I wrote was about climate change impacts, but the recent one I just submitted was about the impacts of natural climate variability. So you can use models to totally remove the human signal and look at how the underlying natural climate system works. So we probe them for a lot of different, with a lot of different questions.
Mm-hmm. Oh,
we're able to. What's that?
Sorry, I just switched to eco, and it actually worked. Sorry, keep going.
Yeah, and basically, so you can treat them like these, controlled scientific experiments where you probe them with different things, and we can use a bunch of different models. So we can use the NCAR's model from Boulder, we can use the NASA model, we can use the GFDL model, all sorts of stuff. There's plenty. There's dozen, 2 dozen around the globe, and you can. They're all coded slightly different, so we can hit them all with the equivalent amount of increased CO2 or whatever your experiment is, and intercompare them and have an actual, controlled scientific experiment with them.
Yeah, it's pretty amazing. I'm really excited for CMYX 6 because I'll be working with one of the models that'll be going into it.
Which one?
The GFDL one. I'm doing one of my projects with their new ocean model, MOM 6. Nice. Pretty excited.
Yeah, Mom's going into CESM out here, so.
Oh, really? Okay.
Yeah, cool. We're moving from Pop to Mom.
Yeah, it's kind of hilarious. I think
know.
MOM stands for like Modular Ocean Model. I don't know what POP stands for.
POP is Parallel Ocean Program.
Okay, they for sure did that on purpose. I wonder which one was first.
It's
I guess MOM was probably first.
Yeah, I'm not sure because POP came out of Los Alamos in like the 90s or so.
I think MOM
80s,
1 was
80s maybe. Yeah.
I think MOM 1 might have been Kirk Bryan's model from like the 60s.
Oh, and he was the OG. Okay.
Yeah.
Yeah, that's cool. Yeah, I mean CMIP 6 is a little slow moving. We have I'm going to this pre-AGU workshop the weekend before, and it's all about CMIP 6 and ocean carbon uptake. And my advisor's an author for the next IPCC report.
Oh, cool.
And for ocean carbon uptake, and she emailed them, and they're like, we need a draft next week, and she's like, the CMIP 6 models aren't out.
Oh my
and they're
gosh.
like, all right, well, write a thin draft for what you think, and then when we get the results, we'll crank out the figures and adjust. But right now, I mean, I know CSM and Boulder, they were having a lot of issues with the aerosol forcing files. I think there was errors in them, so it's interesting because I started looking at climate models well after CMIP 5 was released, or a couple years after, so everything was kind of in motion.
Yeah.
This is my first time to see a CMIP experiment from its origin, and you just watch as the whole community scrambles to run a monster amount of experiments using a lot of computer time. So like at NCAR, we've shut for the most part, most simulations that aren't CMIP 6 aren't being run. All of the computer time's going towards CMIP 6 because it's a big feat to go just from the pre-industrial control all the way up to interesting stuff like decadal prediction runs, which I'm working on now. Oh,
cool! You're actually involved in that? That's awesome.
I mean, I'm involved more with looking at the decadal prediction output, is what I mean.
Okay.
And the only runs I'm doing are down at Los Alamos.
Yeah. All right. Well, thanks for coming on the stream. I'm gonna switch to Echo now.
Cool. I'll watch a little bit. I'm curious to see what it's like.
Yeah. All right. See you later, Riley. Thanks for coming on.
See you, man. Yeah, of course. Thanks for having me.